Hey guys, this is going to be a quick review of calculating an Atwood machine's acceleration, and then also a little bit of kinematics review too, to help you with the lab. All right, so we're going to start with a 1 kilogram weight and a 2 kilogram weight. I numbered the 1 kilogram weight 1, the 2 kilogram weight 2. So for each one of them, we want to do a free body diagram. For the 1 kilogram weight, I'm going to have M1G going down, and I'm going to have T going up. And I'm going to have that T be a little bit longer. And I know that because this is the heavier weight, that this one's going to go down, so that's going to be a positive direction, and this one's going to go up, and that's going to be a positive direction. And this will ensure that all of our answers are positive. On the other one, on the other side, I'm going to have the same tension because I have an ideal pulley, massless and frictionless. So we're going to have T going up, and now I have M2G going down, and I'm going to make this one a little bit longer than that one. And that shows to me that it's a bigger force, which is going to cause that acceleration. So for each one, they're going to have their own F net. The second law applies to each one of them individually. So for this one, I'm going to have F net equals M1A, and then I'm going to take T to be my positive direction because that's my direction of motion. That's what I think is going to happen when these go. And yours are going to be much closer masses. They're barely going to move. That's the advantage of having an Atwood machine. So this is going to be T minus M1G equals M1A. For this one, it's going to be F net equals M2A. And now my positive direction is the weight, because this one's bigger. It's going to cause that one to go down and accelerate. So I'm going to have M2G minus T is equal to M2A. So if I write this below it, I can see that I have a positive T and a negative T. My tension is internal in these situations, so if I add them together, it'll cancel out. And so what I'm going to end up with is M2G minus M1G is equal to M1A plus M2A. I can factor out an A because they share the same magnitude of acceleration because they're connected, like two cars of a train. So I have M2G minus M1G is equal to A, M1 plus M2. So my acceleration ends up being the difference between their weights divided by the sum of their masses. The top of my fraction being my net force, the bottom of my fraction being the total mass. So I chose easy numbers for myself. Whoop. So I have 2 kilograms. Whoa. Smartboard's going a little wacky there. I have 2 kilograms times 10 meters per second minus 1 kilogram times 10 meters per second divided by 1 kilogram plus 2 kilograms, which would be 3 kilograms. So I have 20 minus 10, which is 10, 10 divided by 3, and I have an acceleration's magnitude, which is 3.3 repeating. All right, so if I scroll up, I want to know how I can get another acceleration based on timing this falling down. And those are the two that I'm going to compare. All right, so I'm going to make some room for myself. And I'm going to say that this goes down 0.5 meters. I'm going to time it. You guys are going to do this 5 times in the lab. So let's say that we do it 5 times, and our average is 0.54 seconds. So you do it 5 times, you add those up, you divide by 5. You want to make sure that everything is going nice and smooth. Then I'm going to make a chart. I'm releasing it from rest, so that's going to be 0. I know the distance it goes is 0.5. I don't care that that's down in this case because I really just want to get a magnitude of the acceleration. The direction doesn't matter. The sign doesn't matter to me. And now I have a time that's 0.54 seconds. So now I want to solve for my acceleration. This is going to be my experimental acceleration. The first one we did was our theoretical one. We used the second law to say what the acceleration should be, and we're testing it with this experiment. All right, so remembering kinematics, if I have constant acceleration, and I do in this Atwood machine, I have that x minus x naught equals v naught t plus 1/2 at squared. That's going to cancel out because I'm starting from rest. You're going to release it from rest and time it 5 times. I'm going to multiply by 2, and I'm going to divide by t squared. So I'm going to have 2 times 0.5 meters divided by 0.54 seconds squared. And I got 3.7. All right, so now I'm going to compare these and see how much error I have. And so my percent error is going to take my acceleration experimental minus my acceleration theoretical absolute value divided by my acceleration theoretical times 100. It's going to give me a plus or minus. So experimentally, when I timed it, it was 3.7 meters per second. Theoretically, I said it should be 3.3. And then theoretically, we said it should be 3.3. So 3.3 is going to be on the bottom as well. So I got 0.12 repeating. I'm going to multiply that by 100, and I'm going to get 12.1, so about plus or minus 12%. And that's how you would calculate the percent error.